We are continuing with the tutorial 2 for this semester. As for quiz 3, for quiz 4 also you have this bonus that there are 2 samples to solve for section 10 and for section 20. So let us start with question 1, which is generally multiple choice, true, false, and so on. It was very easy this time because there was only one chapter, the chapter on ceramics. Dash has a BCC structure and a coordination number of 8. Tellurium bromide, zinc blend, magnesium oxide, none of these. It was very simple there that there was the cesium chloride family, there was the sodium chloride family, and there was the zinc blend family. So the first answer, tellurium bromide, if you know from the list, is the same as the one that we did. So coordination number of 8 and BCC structure, it is tellurium bromide, because when you go to the other 2 kinds, they have FCC structure, if you remember. So this is a pretty simple one. And I am just reminding you that tellurium bromide is the cesium chloride family, which is the only one which had coordination number of 8 in the families that we did. Number of anions surrounding a cation in an ionic ceramic is called dash number. So this is very, very simple, right? It is not atomic number, it is not Avogadro number, it is not Boltzmann number. It is just coordination number, right? Coordination number is that in a ceramic, one type of atom is touching how many of the other types. There is anion and cation. So this is coordination number, a very simple one. In the dash unit cell, anions occupy FCC atom lattice sites and cations occupy interstitial sites. So again, right, there were only 3 families, the cesium chloride, the sodium chloride, and the zinc blend. So the cesium chloride was BCC already, right? Cesium chloride was BCC. So you are left with sodium chloride and zinc blend. And in the 2, only sodium chloride family was where it is FCC and the other atoms are in the interstitial sites. So sodium chloride is the answer. Tellurium bromide or cesium chloride or cesium bromide are not the correct answer. Sodium chloride is the correct answer. Ceramics have high chemical stability and high melting temperature. Very correct. These are some of their very important properties. So yes, this is true. In ceramics, bonding is mostly covalent and some ionic. So I have just switched it. If you know that in ceramics, bonding is mostly ionic and some covalent. So this is false. This is the opposite of what it actually is. If the anion touches the cation in a ceramic, then the arrangement is unstable. So where we were talking about stability and so on, we showed you that if the smaller atom is too small to fit the cavity, to fit the interstitial gap, then there will be instability. But if it is exactly touching, then it is a stable one. So this is opposite, right? If it touches the cation, then it is stable. So this is a false statement. With that, we this was an idea of some of the multiple choice and true false. So let us go to question 2A. But once again, there are 2 sections. So this is question 2A of section 10. What are ceramics? What are their main properties? Name some traditional and engineering ceramics. So very simple things. First, define what is a ceramic, then some of their main properties, and then traditional and engineering. So definition, define. Ceramics are inorganic and non-metallic materials bonded together by ionic or covalent bonds. So this is very important. First part also and the second part also, that they are inorganic and non-metallic materials, right, generally. And they are bonded together because in the major categories you have metals and you have polymers and you have ceramics and so on. Main properties, electrical and heat insulation. They are not good conductors, but they are very good insulators for electricity and heat. They are very hard but brittle. Because they are brittle, they have low ductility and low toughness compared to metals. They have high chemical stability and high melting temperature or high temperature resistance. So these are some of their major properties. They have other things also, of course. Traditional ceramics, the basic components are clay, silica, feldspar and so on. So the examples are glass, bricks, construction tiles, electrical porcelain. These are lots of ceramics which are around us, but these are basic traditional ceramics. And rather than saying modern or advanced ceramics, we say engineering ceramics, modern or advanced ceramics. So alumina, silicon carbide, silicon nitride. One or two of you, I don't know, wrote sodium chloride here. Now sodium chloride, you see, has been there since the earth was formed. So it is not brand new engineering ceramic. Sodium chloride is salt, common salt, and it has always been there as a rock salt and so on. So not those, but this, yes. Aluminum oxide is called alumina. Silicon carbide is very critically important. Silicon nitride and so on. So this was a very simple thing. Again, majority of you got it right. Some of you had a small hiccups here and there. Let us go to question 2b for section 10, the second part of the question. Calculate the density of cesium iodide which has the cesium chloride structure. Ionic radius for cesium and iodine is given. Mass for cesium and iodine is given. Mass, of course, is in gram per mole. So it's a very simple traditional question. Again, I would ask you to stop here, solve it again, get some practice, and then continue. So if you are continuing now, then you have already solved it. Density, is mass per unit volume. You know the definition. Mass means the mass of the molecule. It is cesium iodide. So the mass of the cesium iodide unit cell divided by the volume of the unit cell, which will always be A cubed. And right. And this is the cesium chloride structure. So you know that for the cesium chloride structure, root 3a is equal to 2r plus r. You see, because normally if it is BCC, root 3a is equal to 4r upon root 2 and so on. But here there are two different r's. So if you remember, or you can go back and check, root 3a is 2, a small r plus capital R. So therefore a is equal to 2r plus r upon root 3. And that is it. So for a small r, you put the value of one radius. For capital R, you put the value of the other radius. One is 0.165, the other is 0.22. So you find the value of A, right? This is the value of A. Now, this value is okay, but right here I am converting it into centimeter. This was nanometer directly, because the standard unit of density we know is gram per cubic centimeter. So if I leave at gram per cubic nanometer, then the number value is okay, but it will not match any standard units. So therefore I am converting it to centimeter. Next step, we know that in the cesium iodide, cesium chloride, there is only, right, equivalent of two atoms, total two atoms, one cesium atom and one not actually atom, ions, right? Ions. So that is it. There is one cesium and its mass is given. There is one iodine ion, its mass is given. So because it is gram per mole, therefore you divide by Avogadro's number 6.023 into 10 raised to 23. Solve it. It is roughly 4.32 into 10 raised to minus 22 gram. Right. So this is the mass now. This is the mass. So once you are here, you have almost solved it, because the volume of the cube is A cubed. So mass upon cube of this will be the density, right? So the density is mass per unit volume, mass is mass, volume here is A cubed. So you take the value of the mass for A cubed, whatever is A cube that. So now because it is centimeter, so gram per centimeter cube will be your answer, and you can round it off and so on. So it was a very simple problem, already simple, but more simple because you had to revise only one chapter this time. Let us go to 2A of section 20, right? Question 1 is common, multiple choice and so on you do on the Moodle, it is common for all of you. So but question 2, the second question is slightly different for this section, and so this is section 20. Describe the main features of the sodium chloride ceramic system. Draw a sketch of one face of the unit cell. Main features of the sodium chloride ceramic system, right? You know cesium chloride, sodium chloride, zinc valent, only 3 systems we studied. So what are the main points of the sodium chloride ceramic? And then I am not asking you to draw the full cube, not the full cube, one face, only one face. So I am just copying from the slide that it is there in your lecture notes. This is the sodium chloride system. So one is that it is highly ionically bonded. So if you wrote this one thing, it is highly ionically bonded. The other is that it basically has an FCC structure. The third is that the smaller atoms occupy the interstitial sites, right? So you are not asked to draw this, but FCC is this face in the middle. So all those are light blue ones, and the dark blue ones are interstitial between this and so on, right? And very importantly, the coordination number is 6. The coordination number is 6. So if you have written any other detail, it is good, but highly ionic, FCC basically, interstitial sites, and coordination number of 6. If you have done this, then you have done most of the things. If you remembered that magnesium oxide, calcium oxide, nickel oxide, iron oxide belong to the same family, then this is good. And I am just asking this. That you see, this is the full cube. So if you take any one face, then the 4 corner ones and the middle one is one type, so one color, and the interstitial sites are the other one. So I am asking this. So this was the requirement, and any 3, 4, 5 points from here. So this was again a relatively simple question. 2B of section 20. Calculate the planar densities of cobalt oxide on the 111 plane. Cobalt oxide has the sodium chloride structure. The ionic radii for the two are 0.082 and 0.132 nanometer. Show the plane and the intersecting atoms on a unit cell diagram. And I have already given the hint that for the 111 plane, each corner atom is 1 by 6. Corner atom is 1 by 6. So again, right, just for practice, if you were section 20, you have already done it. If you are section 10, then this is a new problem for you. So stop the video, pause the video, solve it, and listen to me after you have solved it. So I have drawn this general. This was exactly one of the examples also in the class. So that this is the 1, 1, 1. So this is the 1, 1 plane, and on this 1, 1 plane, the atoms that it is intersecting, are these atoms, these corner atoms, and these middle atoms. So it is very simple that there are 3 corner atoms, and I have already given the hint that the corner atoms are 1 by 6, and these atoms in the middle are half. This is very clear. The other half is here. So this is half. So 3 into 1 by 6 and 3 into half is 2 anions, right? Is 2 anions. So 2 equivalent atoms are there on this plane.